Hey, what's up, guys? My name is Marabi Hassan, and I'm going to be talking about reinforcement learning in Street Fighter 2. So during this presentation, I'll also be including clips of Ryu, or Ryubot, playing through the Street Fighter 2 campaign, because, I know, it's pretty interesting. So, without further ado, let's dive right into it. So, overview and motivations. Some of the biggest challenges was actually just kind of coming up with a project scope, and what I managed to land on was kind of finding a way to utilize reinforcement learning methods into older games, namely older console games like Genesis games or SNES games. Some of this motivation came from a Medium article I read. It was really cool. It's the guys that made the gyroscope bot, and they basically re-implemented the Street Fighter 2 environment, or they built it themselves, and they implemented their gyroscope bot and managed to win a couple games with it. Unfortunately, I couldn't really find much clips of it anywhere, like on YouTube, so that's something I'll keep researching, but so the kind of market for this is for developers. They can use this AI to basically playtest their game multiple times, see if there's any bugs that break the game. What could also be a really cool market for this is also speedrunners. They could use the AI and kind of see if they can find new strategies to get that world record. So related work. I kind of touched upon this before, was the Gyroscope AI by Street Fighter 2. Like I mentioned, I couldn't really find too much about it, and I think the Gyroscope AI itself is some kind of variation on a DQN or a Deep Q learning network. But someone who has been a huge resource during this project was Lucas Thompson. Lucas Thompson runs a YouTube channel where he talks a lot about reinforcement learning and how to implement those into older generation games. So shout out to Luke Thompson. He's been amazing throughout this whole project cycle. So some of the main questions I had while just doing the project, firstly, could we even do it? Is it even possible? Street Fighter 2 came out in 1991, and it's a beloved game by many, not only for the graphics or how it played at the time, but also its innovations it made, and those innovations would be later used in different fighting games afterwards. So could an AI even learn those patterns for a complex game like Street Fighter? Secondly, it would also be, what type of methods would work best for the AI? Is there different algorithms that work better for the AI? Those are all different things I could play around with. But also, could we use this AI and implement it in different environments? Let's say, if we trained it on Street Fighter 2 for Genesis, could we also train it, or could we also test it in F-Zero, and will it have similar results? So it took me a while to actually kind of figure out what type of environment would be best to actually play these old games. What I managed to settle for was Gym Retro. If you guys aren't familiar, Gym Retro is developed by the OpenAI team, so we did something with it kind of earlier in the year with Frozen Lake, and Gym Retro is a continuation of the gym environments, and you can basically implement a gym environment into an older console game, like let's say Sega, Genesis, or SNES. What's really nice is they come with a library of kind of pre-configured games. So in this library, it includes I believe a data.json file, which includes basically pieces of memory that are useful for the game, like enemy health or player health. It also comes with save states and a way that you could also play the game through a Python API wrapper. And one of the final tools that the Gym Retro guys came out with was an integration tool. So integration tool basically lets you play ROMs and kind of create your own save states, which is really cool if you actually want to implement your own games into this. So I use NEAT. What NEAT is, or what NEAT stands for, is the Neural Evolution of Augmenting Topologies. That's kind of a mouthful, so essentially what NEAT is it is a evolutionary algorithm that is used to change a neural network. I kind of how this works is first there's a population of agents, each with a neural network, and as these agents are playing throughout the game, they're kind of critiqued on this fitness function or this fitness criteria. Agents that make this fitness criteria are kept, while agents that don't make this fitness criteria are cut. And the agents that do make the fitness criteria are then breeded for the next generation of populations. So it's a continuous cycle until you get like the best agents that can play throughout the game. And you can find this base algorithm in a Python package, but since then there's been later adaptations of Neat. There's been HyperNeat that uses different setups, and also DeepNeat as well, which is really cool. So I managed to work with Neat and actually get it implemented into my own local Python. However, the Neat algorithm kind of got stuck. What ended up happening was the agent decided that to get the best amount of reward was to literally just stand still, while the anime just kind of held on him. So from there, I didn't have too much time, so I ended up changing the design into a separate Python package called Stable Baselines. Stable Baselines is the continuation of Baselines, which was a reinforcement learning package made by the OpenAI team. And using Stable Baselines, I implemented the A2C algorithm, or Advantage Actor Critic model, into. From there, since I had to change up that model and I didn't have too much time, what I ended up going for was changing a Python package to, or Python environment, into Google Colab. So Google Colab is basically a Python notebook that is ran on Google's cloud platform. What's really nice about it is it gives you free GPU processing in the cloud. I think the GPU that they come with is a Tesla K80, which is solid GPU. Not only this, but since this is on Google's cloud platform, it's much easier to actually access stuff through Google Drive, and TensorFlow works very nice with it. It's very native with it, so actually running that and analyzing the model wasn't that bad. So finally, this model was trained on medium difficulty for levels, so going through and creating individual save states on each level on medium and having the agent run through it about 1,000,000 times. And while evaluating this model, I decided to do it on easy because that just produced the best results. So our little Ryu bot managed to finish the entire campaign this way, which is very nice. And actually analyzing the footage, I managed to see that he kind of focused on special moves and throws the most, and I think this is because it had the most amount of damage, and it really doesn't take too many frames to actually do a special move, so I think that's why he prioritized those. So for some of the limitations of this project, Ryu is the only trained character. If you had this same AI but trained it on another character such as Kyle, it really wouldn't do that well with him. So that could be something that's implemented in future work. Another limitation of it is the agent only knows how to beat levels less difficult than medium, which really isn't that many levels. So training the agent again, I think it will produce better results using it in a harder difficulty, but that's to be determined. And finally, the final limitation of this was the model is only accessible through Street Fighter 2. So if you were to use the same agent but train it through, or if you wanted to use the same agent for another game like F-Zero, it's not really too possible. But I think there's a lot of things you could do with this. I'm hopeful about the future work that comes out with this. And yeah, thank you for sitting through my presentation. I'll probably also release a full clip of Ryu beating the game if anyone's interested. Thank you.